Yet another take here. This is something that originally appeared in Scientific American 2003 and actually was reprinted in 2012 in Scientific American's special magazine on time. And in this case, the author's talking about relativity, and he says, when the paradox is addressed, it is usually done so only briefly, by saying that the one who feels the acceleration is the one who is younger at the end of the trip. While the result is correct, the explanation is misleading because of these types of incomplete explanations. To many partially informed people, the accelerations appear to be the issue. And when we're talking about accelerations, that is synonymous with general relativity that Born had mentioned in the previous slide. Therefore, it is believed that the general theory of relativity is required to explain the paradox. Of course, this conclusion is based on yet another mistake. Since we don't need general relativity to handle the accelerations, the paradox can be unraveled by special relativity alone, and the accelerations incurred by the traveler are incidental. So as you can see, this is a lot closer to what Wheeler and Taylor say, where you can use special relativity alone and leave general relativity out of it to explain why A slowed down and B did not. But yet, Born says just the opposite. Born says it's not possible to resolve this twin paradox without the use of general relativity. So what do? Well, actually, we can go back and look at what Einstein said. It's his theory, right? So what did Einstein say? Einstein resolved the paradox in 1918 by using a variation of his principle of equivalence that he developed 7 years earlier. He wrote a paper in 1911 that had a lot of very interesting things on it that was kind of a bridge between coming out of special relativity and before he had full-fledged developed general relativity. This recognized acceleration and gravity as additional methods for slowing the rate at which clocks tick. So way in the beginning, we talked about a number of different things that could alter the way that our time or clocks elapse. The thing that we've been focusing on so far for the most part is relative motion. Something speeds up, goes to a higher velocity. According to the special theory of relativity, that is actually going to slow down that clock as a consequence of that motion. But yet Einstein in 1911 also wrote a paper on, said, well, wait a minute, there's some other things at work here that can wreak havoc with our clocks, and that would be separately acceleration and gravity. And we talked a little bit about gravity earlier, where the closer you are to a gravitational field, the more your clock is going to slow down, and the stronger the gravitational field, the more the clock is going to slow down. So if you had an atomic clock sitting on the surface of the Earth for a year, and an atomic clock sitting on the surface of the moon for a year, even though they're both on the surface of each object, the Earth is much more massive and is going to have a more pronounced clock slowing effect over time than the one on the moon. This led to what has famously been called the elevator experiment. And it started in, actually, I think, 1907. Einstein declared as the happiest thought of his life. Most people would think the happiest thought of their life would be, getting married or their kid being born or going to the amusement park or something. But in this case, Einstein's happiest thought was basically realizing, and I think he was falling back in his chair at the time, the way that he recounted it. He slipped, fell back in his chair, and realized that if you were to free fall, whether it was from falling out of your chair or falling off the roof of a building, while you're actually in the free fall, you actually don't feel gravity. You're in the gravitational field, and it's the gravity that's pulling you down, but you actually don't experience gravity for that time period. Kind of makes sense, because I'm standing on the ground, I'm not falling, and I'm feeling gravity. I can feel the force between my feet and the floor beneath it. But if I were falling, I would feel no force. I would be in free fall. So that was, according to Einstein, the happiest thought of his life. And we want to compare that to an elevator in free fall, to an elevator floating in outer space, just to show you what Einstein meant by that. Okay? If this were an elevator car, and this person were transported way out in outer space, not near any kind of gravitational field whatsoever, then that person would be freely floating, just like you see the astronauts floating out in space when they're sending their video images back. And what do you get is, again, you're floating. Nothing is falling to the ground. Everything's just kind of sloshing around, and you're floating in free space. There's no gravity pulling you down. Well, basically what Einstein said was that very same thing would happen if this elevator were actually at the top of a building and the cable and the safety cable were cut and that elevator were free falling. When that elevator went from the 100th floor all the way down to the bottom, for those few seconds that elevator was in free fall, the elevator, the person, and the ball and everything in it would all be falling at the same rate, so it would create the exact same appearance as if you were in outer space. So the good news is for about 5 seconds you'd feel exactly like you'd feel as you were in outer space. The bad news is after 5 seconds the ride's over. So that is the the groundwork to what Einstein referred to as the principal equivalence and drawing a connection between acceleration, or in this case a lack thereof, and also not experiencing gravity. What he did was then kind of flip that around and said, well, what if we do something different? Instead of comparing outer space to free falling, what if we actually compare actually being grounded in gravity? What would happen? Well, if this elevator were actually on the ground on the first floor of a building and not moving, what would happen? The person let go of the tennis ball, the ball would fall to the ground. A little faster than that. Again, we don't have George Lucas. What Einstein determined was that if we took that same elevator car that was in outer space, and instead of just letting it sit there so that you could just float freely, that elevator car was actually attached to a cable and was pulled by a rocket ship. If that rocket ship were accelerating and dragging that elevator along with it, that acceleration would actually be felt by anyone inside the elevator. So if the elevator were in outer space but was being accelerated in this direction, then the floor beneath this person would be constantly pushing up against the feet of that individual, and if it was accelerating at just the right rate to mimic gravity here on Earth, that person would actually swear they're inside of an elevator box on the ground on planet Earth. And the same thing would happen, because if they were in outer space and they let go of the ball, but the elevator were moving upward to meet the ball, it would produce the same effect as the ball falling to the ground, except in this case, the ground is coming up to meet the ball, right? But to that person, they're not able to distinguish between the two things. If they're being accelerated in outer space, then there is actually simulated gravity going on because they're in an accelerating frame, right? And that's what Einstein's principle of equivalence pretty much determined, was that gravity and acceleration, there's a lot of commonality to the two things, and you could kind of equate them. We found out later that it wasn't, everything wasn't equal about the two things, but for our purposes, close enough, right? Well, with all of those things being equal about gravity and acceleration, Einstein was actually able to draw other conclusions about light and clocks. Imagine this same elevator car in outer space being accelerated. So it's in outer space, so before it starts moving, it's a zero gravity, you're floating. All of a sudden, the rocket ship with the cable attached pulls your elevator car, and all of a sudden you can feel the floor coming up, and now you feel actually like you're on the ground, even though you're not in a real gravitational field on Earth, but in simulated gravity because you're accelerating. Well, Einstein said, well, what's light going to do in a case like that, in a state of acceleration? And what light is actually going to do is, depending on where the light source is, you can actually wind up changing the frequency of the light. If we had a big flashlight on the base of the elevator, and the elevator was accelerating upward, then while the light signals were being transmitted from the floor of the elevator to the ceiling of the elevator, then what we would have is the receiver of the light signals up at the top there would actually be moving away while those signals were in transit. So it would actually stretch out the frequency of the light signals and actually cause what's called a redshift. Okay? The opposite thing would happen in the other direction if signals were generated from the top of the elevator there, and when those light signals were sent downward, the elevator, because it's in a state of an acceleration, the base or the floor of the elevator would actually be rushing to meet the signals, and those signals would actually hit the base more frequently or with increased frequency than they were generated from the top. Okay, So you actually have, and it doesn't necessarily have to be a stretching or shifting of light frequencies. Feynman, in his famous lecture on physics books, Richard Feynman even talked about light pulses being generated every second from one source or another. And you can imagine that too. I mean, if this had a light and it just popped on every second, then the receiver of that light signal's up on top. The intervals that it received them would be different than the rate that they were generated down here, because the actual elevator is in motion in an accelerating frame while these signals are being generated. As a result, Einstein determined that something must happen to compensate for this weird effect. And what he said was, time must run faster for the higher clock and slower for the lower clock. Okay? He concluded that clocks in a gravitational field experience the same time dilation as clocks in an accelerating frame of reference. So what he did was, in the previous slides, he used a lot of other examples where he was able to say, you know what, if you're in a state of acceleration, we can observe this, this, and this. If you're in an actual gravitational field, we'll observe this, this, and this, and these things are the same. So what he concluded was, for all practical purposes, gravity and acceleration are equal because they will produce the same equal results. So when he used this light model in an accelerating frame, he then concluded that, well, that must be how clocks work in a gravitational field too. It must work exactly like they work in an accelerating frame, where the higher clock runs faster and the lower clock runs slower. We have a little example here. Watch fast though. That one's going faster, that one's going slower, even in different parts of the elevator, right? So our official resolution is, during the inertial portion of the traveler's journey, his clock will be seen as ticking slower by his twin brother on Earth, while at the same time the traveler will also see his brother's Earth clock ticking slower too. This is an interesting concept here, because this is the inertial portion of the journey. This is from here to here and from here to here. This is where we've got constant velocity. We're not speeding up or slowing down. Here we're either speeding up, slowing down. Same thing here, we're turning around, so here we're either speeding up, slowing down, and over here we're either speeding up, slowing down. But the bulk of this journey is where we've got constant velocity. And if you remember, we had kind of a conundrum, because if all motion is relative, why should one clock have preference over the other? But then it was concluded that clock A, upon the unification with clock B, was running slower. But yet, they were supposed to be on equal footing, because according to Galileo, there is no preferred frame of reference. It's all relative motion. There is no absolute. So why should A enjoy something that B is not? And Einstein's solution to that is, the difference is during these periods of acceleration, because during the constant velocity portion of the trip, what actually happens to one clock will actually happen to the other. Now, the interesting thing about that is, if we take this at face value, what Einstein is saying is, the moving clock will appear to run slower to this poor guy here back on Earth, but the guy's Earth clock will appear to run slower to the moving clock. Now that doesn't make any sense, because usually when there's a difference between two things, the differences are equal but opposite. If I'm taller than you, then that means that you're shorter than I am, right? If I'm heavier than you, then that means that you're lighter than I am. If you're higher on a ladder than I am, then I'm lower on the ladder than you are. So anytime I'm comparing a difference between two things, what's true about one, the opposite will be true about the other, except apparently this, because in this particular case, Einstein is basically saying that in order for this to work and to preserve Galileo's relativity, because again, if Einstein realized that if we didn't do it this way, then there would be something preferred about A's clock just because it was in motion, and that would break half of relativity. So Einstein knew that he had to do it this way. So basically what Einstein is saying is, I'm standing still, I see you flying by me. While I see you flying by me, your clock is running slower. Now you would think then that as I'm flying by, that person would look at me and see my clock running faster.